this is Annika Nebel, live from the iGEM channel. Today we will have a report from Germany's safest laboratory in Marburg. Let's meet the lab members. Good morning, Dr. Steinbach. Do you have a second?
Genetically modified organisms for research and industrial use are generated in laboratories. These organisms are subject to certain strict safety regulations. But what happens in the unlikely event of an outbreak into the environment? The organisms used in this laboratory contain a so-called killswitch system that leads to cell death in non-laboratory conditions. But how is the killswitch built? Our killswitch is composed of 3 interconnected modules which enable the survival of cells under laboratory conditions. However, as soon as a cell is taken out of this controlled environment, the killswitch is activated and kills the cell. The function of Module 1 is the production of 3 components. First, a toxic protein for the perforation of the cell membrane. Second, an essential gene necessary for the survival of the cell by linking the 2 ribosomal subunits, the important protein factory of cells. And third, a regulative protein controlling the third module. Module 2 is producing the antagonist of the toxin expressed in Module 1. In order to keep cells alive under laboratory conditions, the toxin and the antitoxin are needed at the same time. Both genes are regulated by a synthetic compound which is not available in nature. This compound activates both Module 1 and 2. In the absence of this compound, as it is the case in nature, both modules are shut down and the cell dies by the lack of the essential gene. Furthermore, the absence of the regulatory unit of Module 1 activates Module 3, which consists of 1 protein clumping the ribosomes together and thereby inactivating them. In laboratory conditions, the essential gene is functional. Both toxin and antitoxin counteract each other and the regulatory unit inhibits the activation of Module 3. The 3-step design of our killswitch guarantees a stable system even though mutations leading to changes in the killswitch components may occur. The following 3 scenarios visualize this circuit. Scenario 1. In the case of inactivation of Module 1, the absence of the essential gene as well as the regulatory unit leads to non-functional ribosomes, resulting in cell death. Scenario 2. If Module 2 is no longer working, no antitoxin is produced. This results in the destruction of the cell by the toxin. Scenario 3. A mutation in the regulatory unit causes the activation of Module 3. Thereby, the ribosomes agglomerate and lose their functionality in any situation. The iGEM team Marburg designed a killswitch system which enhances safety for humans and for the environment. Our research follows the tenets of safety first.